Hi, boys and girls. So I just want to address a few points related to this table here. It's called the standard reduction potential table. So you'll be provided with this table on the test. Please know that I'm not doing a video on every aspect of the ISA. It's your responsibility to make sure that you read all these sheets thoroughly, but I'm just highlighting some things that in the past students have had difficulty with. So just want to go over some things on this table. So this is a table that shows you the reduction potentials of different half cells relative to a standard. So it would be impossible for us to build every possible electrochemical cell with every possible redox reaction out there. What we're interested in finding out is what voltages we can expect, but we'd have to assemble all kinds of different electrochemical cells and calculate their voltages. Instead, and that would be onerous. Instead, what scientists have done is they've determined a standard, because you can't measure the potential of a half a cell. It can only be of a full electrochemical cell. So they decided on setting a standard reaction against which all other cells would be, half cells, I guess, would be measured. And the standard reaction that they chose was this reaction here, the reduction of hydrogen. So this shows two hydrogen ions reacting with two electrons, accepting two electrons. This is a reduction. In fact, these are all reductions, and forming hydrogen gas. And we assign this value a value of 0. And so what they did is they built cells, electrochemical cells, where every one of the reactions that you see here is combined with this specific half cell. Okay, and because this is assigned a value of 0, whatever voltage reading they get when they combine each of these half cells with this hydrogen half cell to create a full electrochemical cell, this half cell is assigned 0, so whatever voltage reading they get, they assign to the other half cell. So notice that the values are positive, very positive here. The most positive value is at the top, and the most negative value here is at the bottom. So what does that mean? These are all written for reduction. So if you do a half cell where this reaction happens in one half cell, and then this is the other reaction, they're both shown as a reduction. They can't happen both as a reduction. So the potential to be reduced is most likely when the value is positive. The more positive the potential, the more likely the reaction will occur as shown. So the potential of fluorine to be reduced gives a voltage of 2.87. This one is 0. So in combination with hydrogen, it's the fluorine that will be reduced, and the hydrogen will actually happen in the other direction as an oxidation. Because remember, in a redox reaction, we need an oxidation and we need a reduction. You can't have two reductions, even though this table is only showing reductions. When you're trying to figure out the voltage of an electrochemical cell by combining different reactions from this table, now that everything's been compared to hydrogen and we have the values, we can compare anything to anything else because we have the individual values and we can figure out the voltage for that specific combination. But the way you know but because they're all shown as a reduction, it's just convenient to do it that way. To decide which is going to be the oxidation, it's going to be the one that's the less positive value, or another way of thinking about it, the one farther down the list. So if you combine, for example, gold with hydrogen, by the way, this is a one-column table that's shown in 2 columns, so it would just continue down if this paper was longer. So it's shown in 2 columns, but really it's a continuation here, okay? This continues from the bottom. So if you combine this reaction, this gold reaction, gold ions picking up 3 electrons with the hydrogen, it's gold that will be reduced because it's got a more positive potential. This one is 0. And so this would happen as the oxidation. It would need to be flipped, and the potential we would get would be 1.5 for that, okay? Positive potentials lead to spontaneous reactions, and you'll see why in another unit later on. Okay, so what if, however, we took the hydrogen half cell and we combined it with nickel? Well, the nickel has a negative 0.23 potential to be reduced. Hydrogen's value is 0. Hydrogen is more positive. Nickel will therefore be more positive in the other direction. If I flip this reaction, I flip the sign of the potential to 0.23, so it's more positive for oxidation. So it would be the hydrogen that would be reduced, greater tendency to reduce, and the nickel would actually be oxidized. Nickel would turn into nickel ions plus 2 electrons. It would happen the other way around. I don't have to combine these with oxygen sites, I kind of alluded to before. Now that I have all the potentials for each half cell measured against hydrogen, because they're all measured against the same standard, now it's a fair to measure them against each other, and I would get the voltage. So if I ran a reaction with this substance here, cobalt, I don't know, and this one, cerium, it's the cobalt that it has the more positive value for the reduction. It's higher up the list, in other words. And so this reaction would happen as the reduction. This one would need to be flipped and happen as the oxidation. And so this would become negative 1.7. When you add those two values, you get the potential for that combination of half cells, the cell potential overall. And so it would be a positive value. As long as you combine something closer to the top of the list with something at near the bottom of the list, you'll get a positive potential. I want to also use some other terminology here. Fluorine here would be, it has the greatest tendency of everybody on this list to be reduced. It experiences reduction. And it has the greatest tendency to experience reduction. Remember that the substance that experiences reduction is the oxidizing agent. So on this side, everybody on this side of the table, the left side of the reaction, I apologize, of the reaction, so left side, and then everybody on the left side here of these reactions would be oxidizing agents. And the if you combine, two oxidizing agents, F2 and H2O2, in actuality, H2O2 is a worse oxidizing, not as good an oxidizing agent, I guess, as F2. So it would actually be forced to be reduced, and this is going to, to be oxidized, pardon me, and this would be reduced, as I was kind of alluding to before. Substances that are on the product side of all the reactions, we would call reducing agents, because they would be themselves reading the reaction that way, oxidized, okay? So whenever you want to build an electrochemical cell, you always want to make sure that you have, let's just circle these or put a square around these. So because bromine, the oxidizing agent, is above magnesium, the reducing agent, when you have this, like I could draw a diagonal line between them, let's just say, that would result in a positive cell potential, and the reaction between them would be spontaneous, okay? If I were to try to pick, let's say, lead over here, this reaction involving lead and water, see how the reducing agent is above the oxidizing agent? It would be a diagonal line going that way. That would lead to a negative cell potential, and that would not be spontaneous. So if you look at this value, this would need to be flipped for the reaction to go that way. And then this one here is going that way, so it would stay the same, but that would be a bigger negative. So you always want to, the reaction that occurs is always between the strongest oxidizing agent, highest up on this side, and the lowest reducing agent on the other side. So I'm mentioning this because there's an activity that you'll do or an exercise that you'll do where you have to consider what's in a solution and decide which reaction is most likely to occur. So you want to find everything that's in your solution and then locate who's the best oxidizer or oxidizing agent highest on this side of the reaction, the left side of the reaction, not the table, careful. And then you want to find who's furthest on the right side of the reaction. So this is, you could have these two substances, for example, that you're trying to react, or you can have silver reacting with sodium. If you had a choice between silver reacting with peroxide and silver reacting with sodium, it would reacting with sodium would produce the more spontaneous potential, because there'd be a greater difference in potential between them, because sodium is further down the list. So remember that this table continues, right? This column is really underneath this one. So I think that's it. So all of that is kind of described in these subsequent handouts. So I think I covered more or less what I wanted to cover, and you should be okay in understanding how to use this table. Thanks, guys.